Let's start with light as a series of perfectly parallel, infinitely long beams tearing through the dark void. When these rays strike a concave mirror, a surface curved inward like a bowl, they don't scatter. The geometry of the curve forces them to pivot toward one another. Every ray intersects at a single absolute coordinate called the principal focus, or point F. The principal focus is the specific point on the principal axis where rays parallel to the axis meet after reflection. The line passing straight through the center of the mirror and this focal point is the principal axis. This is the core function of a concave mirror. It gathers a wide spread of parallel light and compresses it into a single focal point. Change that geometry to a convex mirror, curved outward, and the light behaves differently. Instead of converging, the rays scatter away from the axis. Our eyes trace these diverging rays backward, creating the illusion that they originated from a single point trapped behind the mirror surface. This is a virtual focus. If the incoming rays arrive at an angle rather than perfectly parallel, they converge on the focal plane, a two-dimensional surface passing through the focus, perpendicular to the principal axis. Whether the focus is real or an illusion, its position is never random. How do we mathematically predict this exact coordinate without having to trace the path of every individual ray? To find the rule, we have to simplify the system. We'll look past the swarm of light and analyze the path of just one incident ray. First, we mark the pole, or point P, the exact geometric center where the mirror meets the principal axis. Since a spherical mirror is a section of a sphere, it has a center of curvature, point C. This is the center of the original sphere. We track a single ray traveling parallel to the axis until it strikes the mirror at point M. To see where this ray goes after impact, we need the mirror's normal line, the line perpendicular to the surface at point M. Line CM is our normal. The incidence angle, theta, matches the reflection angle, bouncing the ray through focus F. Parallel lines create a Z shape, making angle C also theta. In triangle MCF, exterior angle F equals the interior angles combined, 2 theta. These precise angles locked the focus into a fixed position relative to the center of curvature. To convert angles to distances, we drop a line from M to the principal axis, creating point D. This forms two right triangles. We define their tangents, opposite over adjacent, for theta and 2 theta. However, this math only stays simple if we use paraxial rays. Paraxial rays are beams that strike the mirror very close to the pole. For small angles, the tangent and the angle are virtually indistinguishable. By substituting angles for tangents, the height MD cancels out. The focus distance is exactly half the distance to the center. Physicists rely on this paraxial assumption as a tool. It simplifies the complex trigonometry into a linear relationship for real-world optics. We have one final step. Our equations use point D, but all standard mirror measurements must originate from the pole, point P. Because paraxial rays strike so close to the axis, the gap between D and P is microscopic. For all practical purposes, we can ignore it. The distance from pole to focus is the focal length, lowercase f. The distance from pole to the center of curvature is the radius of curvature, uppercase R. This completes the derivation. For any spherical mirror, focal length is exactly half the radius. We apply this using the Cartesian sign convention. Distances measured against the direction of incident light are negative, as in a concave mirror, while those measured with the light are positive, as in a convex mirror. The formula F equals R over 2 allows optical engineers to design massive space telescopes with absolute total certainty. They don't need to test every mirror with a laser. They know the focus based purely on the physical curve of the glass. The same rule governs the convex security mirrors in shops. The virtual focal point is locked in by the radius of the plastic dome. The result is a single geometric rule that resolves the chaotic scatter of light into a highly predictable coordinate.